accuracy, precision, and recall. The confusion matrix provides us this detailed information, but sometimes it's nice to have a concise number, 15%, 90%, 80%, things that you can easily communicate to either clients or coworkers about the accuracy of a model. So first, we're going to do that by defining the term accuracy. And that's going to equal the number of correct predictions over the total number of predictions. Or another way to say that is accuracy is equal to true positive plus true negative over true positive plus true negative plus false positive plus false negative. So while accuracy definitely offers valuable insights, it's essential to consider that the number of falsely classified positive and negative predictions, especially within the context of what's listed above, are not going to greatly affect it, right? And so for that, we want to look deeper into the accuracy definitions. And let's define two more things that will help us clarify some of these specific cases where the false positives and false negatives aren't fully taken into account. And for that, we're going to define precision. And that measures a fraction of selected relevant instances over selected instances. And recall is the selected relevant instances over relevant instances. So before we look at a graphical diagram of this, well, actually, let's look at the graphical diagram first, and then we will define a few terms. I like the graphic. So this is what we are trying to decipher here. Word actual spelled wrong, but that's okay. So, yeah, it's like, it's a math term at least. So we have relevant instances. That's what's going to be on the right-hand side here. So these are actually true instances, and they're denoted by kind of an orange circle. And then we have the actual false instances, so actually not true, and those are going to be blue circles. And then we have our selected instances. And then we have our, that's not supposed to be there. That figure is updated in the text. I don't know why it's not here, but that's okay. And then we have our selected instances, which is what's inside of the circle, right? So precision is going to be true positive over true positive plus false positive, right? So it's going to be true positive over true positive plus false positive. And recall is going to be true positive over true positive plus false negative. So one way to achieve perfect precision is to make only one positive prediction and to ensure that it's correct, right? If my instances are so constrained that I only have one positive prediction, then I have perfect precision. Is it very useful if my model only makes one positive prediction? No, right? It's probably something that's so far out there that it was absolutely easy to classify, and the things that we're interested in classifying are going to be closer to the line. However, that approach, right, would be impractical. Kind of ignore most of your items of interest, right? So recall is also known as sensitivity or true positive rate, and it is the ratio of true positive to true positive and false negative. And each one of these terms have something that you can mix and match to get them to line up. All of these, you want a high ratio, right? 1 or 100% if you want to put it in percent. That's the goal. The goal is to have 100% accuracy, 100% precision, 100% recall, but you won't have all of that on everything. So it can get a little bit confusing to always be thinking about these three numbers. So we like to simplify things down even more in machine learning, and that's to just give you an F1 score, which is just equal to 2 times precision times recall over precision plus recall, which is equal to, if you cancel out a few terms, true positive over TP plus false negative plus false positive over 2. And that's going to be your F1 score. And an F1 score is a wonderful thing to report. And typically, if you're, say, writing a paper or trying to show someone that a machine learning model is working, report the F1 score first. And then below it, report the things that make that up, the accuracy, the precision, and the recall. All right, so how can we tune our accuracy, precision, and recall to get what we want? And we can do that by starting to move our threshold, which is where we want to draw the line, right? There's this somewhat humorous poster board from PETA that says, where do you draw the line between food and pet, right? And people draw at different places. But we're kind of looking at the same thing here, right? So where do you draw the line? And that's going to change your precision, accuracy, and recall. So now that we have metrics for accuracy, precision, and recall, which are all going to be very helpful, we can talk more about the threshold and how making differences in how adjusting the threshold of our regularized linear classifier will give us different solutions. So if we take this x-axis here to be our score, and everything to the right is going to be a higher score, right? So this is high, and this is low. Every value here, every digit here is going to get a score, right? And so let's just say, for lack of or for clarity, this has a score of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So on all 12 of these, now we can move our threshold where we want, right? So again, if we think back to the definitions, accuracy is our true positive plus our true negative over everything. And so if we put our threshold here at about 3.5, we get an accuracy of 75%, which doesn't sound so bad because we have 9 true positives. We have 1, 2, 3, 4, 5, 6, 5 that are classified as a 5. And we have 3 true negatives, 3, 2, 7. And what's misclassified here with this threshold there are this 3, 8, and 3. But those aren't counted for in the accuracy, at least not in the numerator. They are in the denominator. However, if we think about it, at the same time, what we have is a recall of 6 out of 9, right? And we get a recall of 6 out of 9 because recall is true positive over true positive plus false negative. So then on my recall for this threshold, right, recall is true positive over true positive plus false negative. So my recall for that is going to equal 6 over 6 plus 0, which is equal to 6 over 6. So if I have a threshold here, I have a 100% recall, right? Which is pretty good. Again, the recall is just the left-hand side here, or the relevant instances. So if I have a very low threshold, while I have a relatively low accuracy and precision, I have a very high recall, right? And what's important here is I'm not missing absolutely any 5s. All 5s are correctly classified. So if you have something like medical diagnostics, this would be a very good place to put your threshold, right? You would rather misclassify a few positives than miss a negative. Now, if you are a credit card company, where you put your threshold depends on how much you charge for your annual membership fee, right? If you're American Express and you charge $5,000 for a very fancy card, the last thing you want to do is detect fraud when it's not fraud, right? Because people are making big purchases and they want their purchases to go through. If you're like me and you have a plastic card from Chase, we can detect fraud all day long because all you're doing is taking away poor people's time, right? So some of these things kind of vary depending on like the products that you're trying to sell. So this happens to be perfectly classified, so right down the middle. If we put this there, we have a perfect accuracy, a perfect precision, a perfect recall, and a perfect F1 score. Everyone always wants that. But in truth, there's very few data sets that you actually can perfectly classify, and you can't do it with the MINS data set either, right? There's always going to be some misclassification. For no other reason than I believe that some of the labels are just simply wrong, right? I mean, some of them just look like scribbles. So they say it's a digit, but it is what it is. And then if we move the threshold even more to the right now, we're very concerned about not having anything that's not a 5 classified as a 5. So this might be an application like a credit card where you have fraud and you have very wealthy clients and you don't want to, you don't want to declare fraud when someone's traveling around the world, right? Because these people tend to travel more. So they tune their threshold all the way up, right? So here your threshold is going to be 9.5, and then you're going to have a accuracy of 9 over 12, which is 75%, which isn't too bad. A precision of 100%, right? Which sounds pretty good, but remember that precision is just true positive over true positive plus false positive, right? And so you have 3 true positive, you have 3 false positive, and you don't care about any of the negatives. So you can get a very high precision, but you're going to miss a few. And recall, right? That's what you recall considers your false negatives, right? And so recall is going to be relatively low here at 50%. And then you get an F1 score of 67%. And again, F1 scores are just a way for you to kind of look at all of this in its totality and judge how good it is, right? Because precision, recall, you have to think about. F1 score, you're always just trying to make 100%. That makes sense? So what does this look like on our MINT data set? So if we take that and solve it on the whole data set, we get something like this. So now the threshold is not 0 to 12, right? It's negative 60,000 to 25,000, but that's okay. And then what we have here is precision and recall, right? So if I set my threshold all the way down here, I have a very high recall and a very low precision. And that makes sense, right? If I put my threshold all the way to the left, I can adjust for precision or recall. And then as I move my threshold to the right, I start to get some changes. So here I have, in exchange for reducing a little bit of my recall, I get a much higher precision, right? And as I move the threshold all the way to the right, now I have ultimate precision and very bad recall, right? If I have 10,000 data points and I classify one correctly, but I only classify one, I've got 100% precision, right? Not bad, but not very useful. And then this green dotted line that cuts in between is my F1 score. And so for this particular model that I trained and ran, I could get like an 81% F1 score. Not great, but not great, right? No way around it. But you can see how the F1 score is kind of a trade-off between precision and recall. So when people are asking you to quantify models, the way to do it is just to ask people about their F1 score, right? It's a very simple method. And like in the projects that you have, you would kind of hope that people are paying attention. And if you're not reporting an F1 score, then they're asking an F1 score. And that just means that the person who you're presenting to understands something about machine learning. Because whenever you try to look into precision and recall, you're going to have a back and forth conversation, right? So the F1 score is a way to mitigate that conversation. Another plot that I like is just to plot precision versus recall on a single axis, and this can help you understand your data, right? This is a great data processing tool. So I can train a model, and here I can plot my recall versus my precision. And I can see for this particular model, which is also the MINT data set, as I train my model, it's quite easy for me to have high precision, which makes sense because all I have to do is correctly classify one thing on the far right, right? But it's actually more challenging, let's say, for me to have, high recall, right? So, and you can kind of see it swing down like this. So, but overall, it's not really so bad, I guess. When I have a precision of 0.5, I have a recall of 1, and when I have a recall of 0, I have a precision of 1. So they're not always going to be like a perfect trade-off in between the two. And looking at this precision recall curve can help know how movable and robust moving your threshold around can be. And generally, you're looking for something that just cuts through, like, you'll never get it, right? But you're looking for something that cuts through like that at a 45-degree angle. So, well, I shouldn't say that's what you're looking for, but that would be a data set that that would almost just be a toy data set that's very linear, right? And very easy for you to distinguish and classify things.